So let me just share my screen here. All right. So this is what we call the Ethernet switching, and it's not very far. I mean, almost everything we have said. The only thing that is going to change here is that now we are going to look at the MAC address in details, and we shall also talk about the switch. When you talk about switching, you must talk about the switch. When you talk about switching, you must talk about the switch. And so you can see we are still going to talk about the frame a little bit, and then we talk about the MAC address. It's all called the Ethernet MAC address. How is it created? Remember, how is it that all the devices, you guys have amazing devices. Some have used Techno, some use Samsung, some use Infinix, you know, some of our TVs are Samsung, some of our TVs are, I don't know, I don't know how they call the other TV. There's Sony. We have laptops, you know, we have HP, we have Acer, we have Dell, Lenovo. We have every equipment, mobile phone, desktop computer, any electronic has a unique physical address, MAC address, band-in address. And so we will talk about a special type of table found in the switch. And this is the basic functional unit of this. It's like human beings having a brain. Without the brain, we can't think. So the MAC address table is a very special type of table found within MAC addresses, right? I mean, found within switches. In fact, if you remove the MAC address from the switch, the MAC address table from the switch loses functionality. The switch loses functionality. And so it is important that we need to learn about how does the switch use the MAC address table to do the job that it does best. And finally, we look at switch forwarding methods and switch speeds. So let's get started here. We, of course, talked about, we said that the data link layer is divided into two layers, two sub-layers. We have the LLC, the logical link control sublayer, and the media access control, the MAC, the media access control sublayer, all right? And then, of course, we have the physical layer there. So because we are talking about the Ethernet protocol, which normally operates within the data link and the physical layer. So the Ethernet is basically a family of network technologies defined by IEEE, the Institute of Electrical and Electronic Engineers, and the code is 802.2 and 802.3, where 802.2 is implemented on the LLC, and the 802.3 is implemented from the MAC, the MAC sublayer, downwards to the physical layer. And so it's important to look up, let's look at the Ethernet frame, you know, a frame that is specifically for the Ethernet technology. Now, what is important to note here, number one, we need to know what is the minimum size of a frame and the maximum size of a frame. So any frame must have a minimum size of 64 bytes actually. So 64 bytes is the minimum size of a frame, and the maximum size is 1518, all right? The 15 added on top, of course, provides some, you know, some control functions over there. But what you need to know is that any frame that is less than the minimum, less than 64 bytes, has a name it's called a rand frame. It's a rand frame, and anything less than the minimum, by the way, will be dropped by the network or the network device or the switch. So a frame should never be less than 64, because if it is less than 64, we call it a rand frame or a collision fragment frame. Now, What if a frame is more than the maximum? Any frame more than the maximum is called a jumbo frame, or it's called a baby giant frame. A baby giant frame. So jumbo frame or baby giant frame. Okay. And that is, of course, very important for us to note. So a frame should not be less than minimum, and a frame should not be more than the maximum. Should not be more than the maximum. All right. So down here, of course, you can see the fields that we've found normally within the frame. We have them. Just a minute. Let me just connect my earpod here. All right. Okay. Okay. Can I confirm if you guys can hear me clearly? You can hear me well?
Yes.
All right. Thank you. So I was just saying, look at the bottom here. We have some of those fields that we're able to see. Of course, instead of having start of frame and end of frame, we have something called the SFD. SFD means start of frame delimiter, and the preamble. Basically, these ones tell us the beginning and the end of the frame. Instead of having addressing, we have this destination MAC address, and we have a source MAC address here. And instead of having the type, which is the type of layer 3 address, we have, type stroke length here. And then the data we are carrying here, which has the maximum size here. We have the data here, which is actually the packet. And then we have, for checking errors, we call it the FCS, frame check sequence, frame check sequence. So again, different fields that we have for the Ethernet frame. Now, the most important thing to note, by the way, is the minimum and the maximum, and the name of each, the name of what is less than the minimum, and the name of what is more than the minimum. Collision fragment or a rand fragment, a frame less than 64 bytes, and the jumbo or baby giant frames, a frame that is more than the maximum. Now, yesterday, if I remember very well, we were able to say that it is only IPv6 addresses and MAC addresses that use hexadecimal numbers, all right? And we say that an IP version 6 address was having 128 bits, but it uses hexadecimal numbers. Now, a MAC address has 48 bits of zeros and ones, but it is expressed in form of hexadecimal numbers, 12 of them actually. So every MAC address has 12 hexadecimal numbers. We can actually confirm with mine here. Let's look at the MAC address of my PC. I do IP config space /all, and you can see that my MAC address is actually here, right here. Sorry about that. Okay. So this is my MAC address. You can see it has 12. So 2 times actually 6 is 12. It has 12 hexadecimal numbers, 84-1B-77-64-1A-D5. One of the challenges I'm going to give you guys, I want you to note how to know the MAC address of your mobile phone. Very important. Also, get to know how to see the IP address of your mobile phone. Those are very important things to know. As an IT guy and as a person in this field, you need to know how to do that. All right. So the physical address is the MAC address. It's normally made of hexadecimal numbers. When you see 8 here and 4 here, those ones are hexadecimal numbers. Those ones are not decimal numbers. You can see B, you can see A, D, so on and so forth. And all computers have a unique MAC address, and the MAC address comes with your device from the manufacturer. And that is that. Now, so the MAC address, like I told you, and we have already seen one. How do we know a number is a MAC address? Sorry, it's a hexadecimal number and it's not a decimal number. So to identify hexadecimal numbers, either you will see a number that begins with 0x. When you see 0x 73, it means this 73 is a hexadecimal number. It is not a decimal number. Secondly, if you see a number written, but it is followed by a H capital, 73H, even that is a hexadecimal number. The last method, if you see 73 with a subscript 16, you know, we have superscript and subscript, where superscript is like, if you say superscript 16 of 2 or of 73, it means it is 73 raised to power 16. That is, 16 is superscript if it is raised to power 73. But when you raise it downwards, you put it at the bottom of 73. Now that is called a subscript. We call that a subscript. So a number written with sub 16 is also another way of representing numbers in form of a hexadecimal number. So I've shown you 3 ways of identifying hexadecimal numbers. Now, let's talk about this. How is it possible? How is it possible for every vendor in the world, Dell, HP, Lenovo, Techno, Huawei, Samsung, Sony, all of them, you can name them. How is it that they are able to assign their gadgets unique MAC addresses which can never conflict throughout the whole world? How do they do that? Here is how they do that. You know very well that the government of any country produces unique identification cards to every of its citizens, unique registration number plates for vehicles, unique driving license numbers for every device. So what happens? So let's see what happens. So what happens is that since the MAC address is made of 6 hexadecimal numbers, the first, 12 hexadecimal numbers. Sorry about that. A MAC address is made up of 12 hexadecimal numbers, as we have seen for my computer. So if the MAC address is made of 12 hexadecimal numbers, the first 6 hexadecimal numbers will be provided by a common organization, a standard organization, and that organization, the vendors must register their device with IEEE, the Institute of Electrical and Electronic Engineers. Okay, so all the vendors must register with IEEE to get the first 6 hexadecimal numbers, which is called OUI. OUI in full is organizationally unique identifier. Organizationally unique identifier. All right. That is given by IEEE. Once the vendor has been assigned the first 6 hexadecimal numbers, then the vendor is now free to create the remaining 6 by itself. So clearly, you and I can see that whether 2 vendors assign the same last 6 hexadecimal numbers, it doesn't matter because they received the first 6, which is unique throughout the whole world. So IEEE registers all the gadgets throughout the world, and it gives them a unique OUI for the first 6 hexadecimal numbers. And that's how MAC addresses remain unique throughout the world, the world, regardless of the vendor, regardless of the vendor. So 3 types of MAC addresses. We have what is called a unicast MAC address. Unicast MAC address. So a unicast MAC address, this is a MAC address that is used for one-to-one communications, just like we saw in unicast IP address. So for one-to-one communications, we use what is called a unicast MAC address. One-to-one, one device or one gadget to another gadget. All right. We have what is called a broadcast MAC address. A broadcast MAC address is a MAC address. It's a MAC address that is used to communications for one to all. So one device wants to communicate with all the devices on the network. It's gonna use a broadcast MAC address. So the broadcast MAC address, you can actually identify it. How do you identify it? The broadcast MAC address will contain all Fs. Everything will be F, as I have highlighted on this slide here. When a MAC address has all Fs, then we know that all the bits will be ones. So that is a broadcast MAC address. So we have seen unicast, you've seen broadcast. You can't identify unicast. Unicast is like the MAC address of each and every device, but the broadcast is used to communicate to all the devices, so it's not for a unique device. The last one, of course, is the multicast MAC address. The multicast MAC address, this is used for communication from one device to some of the devices, just to a group of people, not everyone else, but just to a group. So PC1 says, I need to send a group of hosts on the network. So just the first 3 devices will actually be receiving the message and not these other 2. So that is a multicast address. How do you identify a multicast address? A multicast address should have this, when you see numbers that follow 01005E, all right? 01005E, this is how you identify a MAC address, okay? When this is part and parcel of the MAC address, 01005E, that's how you know this is a MAC address. This is a multicast MAC address. That's a multicast MAC address. Ladies and gentlemen, it is that time when now we have talked about the MAC address, and now we need to talk about the switch. The switch has a special type of table, and the switch makes very good use of the MAC addresses. And the fact that every PC has a unique MAC address, that makes work easier for the switch. That makes the work easier for the switch. The fact that all the MAC addresses are unique or are supposed to be unique, that makes work very, very easier for our switch to do its work, right? And so it's important to note that the switch has a special type of table, and we call that table a MAC address table. We call that table a MAC address table. Why do we call it the MAC address table? We call it the MAC address table because it stores 2 things. It stores 2 things, and one of them is none other than the MAC addresses. For every PC that connects to the switch, I mean, I want you to know that every time you go to any computer lab, every computer in the lab there connected with a cable, that cable goes to somewhere in the switch. It actually runs to a switch, not a router, all right? And so this table is a special table, and a switch without this table is nothing, all right? This table is called a MAC address table. The other name is the CAM table, the content addressable memory, the CAM table, the content addressable memory table. Now, what we want to do right now is we want to look at how does the switch use the MAC address to do its job. How does the switch use the MAC address to do its job? Okay. Now, when the switch is just turned on, the switch was off, and you just give it power. initially the MAC address table is empty. The MAC address table is empty. And then the switch now begins to learn. The switch now begins to learn MAC addresses of different PCs. So this is that time when now I want to switch you guys to this screen, and I want to use your hearing ability to test if you can hear this video. Just tell me if you can hear what is playing here. Can you? Can you hear?
No, no.
Oh, okay. Okay. Let me just do this again because I need you guys to hear it. I need you guys to hear this. This is very, very important. Okay. Okay. Just stop sharing. And I'm gonna share this again. This time around, I want to share a specific window here. And I'm gonna share this window here. Oh, not yet. Not yet. Stop sharing. I'm gonna share again. I include computer sound. The sound. And this is content from camera. Now file. I browse my computer. Okay. Share content. So I want to share this one here. Just confirm to me if you can hear this again.
Ethernet frame to PCA. We're going to examine how switches S1 and S2 build their MAC address.
Do you hear anything?
Yeah.
Yes. Yes.
Wonderful. We need that. We need guys. I need you guys to hear that because it's important. So we are going to learn, basically starting from here. We are going to have a device. This is actually a switch. This is a switch. And we have PCs here, PC A, PC B, PC C, and PC D. And these PCs are directly connected. They are connected to the switch. And each PC is connected to a port. So PC A, for example, we are using short MAC addresses, basically for experimentation purposes. Otherwise, a MAC address cannot be 000A. It must be 12 hexadecimal numbers, as I've told you guys. So we're using short MAC addresses for explanation purposes. So what you are going to learn is that every time a PC is connected to the switch, in the MAC address table of the switch must store 1, the MAC address table of this PC, 2, the port number of the switch. Remember, like the switch we have been talking about normally has 24 ports. First Ethernet 1 to first Ethernet 24, and then G1 and G01, gigabit Ethernet 1 and 2. All right. And so the thing is, I want us to look at this video here, and I want us to just basically learn something from here. It's a lot to learn here. So let me just play it as you listen, and you're gonna ask me questions, or you can interrupt me, and I'll pause the video so that you can be able to understand how does the switch build the MAC address table. How does the switch build its MAC address table? And how does the switch forward frames based on the contents of the MAC address table? So let's listen in.
In this video, PCA is going to send an Ethernet frame to PCB, and PCB is going to send an Ethernet frame to PCA. We're going to examine how switches S1 and S2 build their MAC address tables, and also how they forward frames based on the information in those MAC address tables. PCA has an Ethernet frame to send to PCB. The source MAC address of the frame is 000A and the destination MAC address is 000B. The Ethernet frame is sent to switch S1. S1 receives the Ethernet frame, examines the source MAC address, and notices that this MAC address is not in its MAC address table, so it adds the MAC address and the incoming port number.
I hope you saw that. One thing I want to emphasize is that the frame has a source and destination MAC address. The frame is moving from PCA with the MAC address of 00A, and the frame is moving to PCB, MAC address is 000B. All right? The only thing that the switch stores on the MAC address table is the source MAC address, not the destination. So if PCA is sending to PCB, only the MAC address table of PCA. The person sending is the person, or the PC sending is the PC whose MAC address will be stored on the table. For us to store the MAC address of PCB, PCB must be sending something to the switch. So do note that. So port number is F1 and the MAC address of the sending device is 008. Let's listen in, guys.
Next, switch S1 examines the destination MAC address and notices that this MAC address is not in its table, so it floods it out all ports. PCB receives the Ethernet frame, examines the destination MAC address against its own MAC address, and notices that that is a match and receives the rest of the frame. The Ethernet frame continues to be forwarded to switch S2. Switch S2 examines the source MAC address of the frame and notices it is not in its MAC address table, so it adds the MAC address and the incoming port to its MAC address table. Next, switch S2 examines the destination MAC address, notices that is not in its MAC address table, so it floods it out all ports. PCC receives the Ethernet frame and its MAC address does not match the destination MAC address of the Ethernet frame, so it does not accept the rest of the frame.
I have a question for you guys. I have a question. Switch S2 has received the same frame from switch S1. The source MAC address was 000A, and switch S2 has stored it on the MAC address table, and it has also stored the port number here. So my question is, which port number is this? Is it port number for S1 or S2? This port number 1.
For S1.
Someone? Very good. The port number is for S1. The switch records the port number through which the message came, through which the frame came. So the frame came into S2 through port 1. That's correct. So let's move on.
The router receives the Ethernet frame, examines the destination MAC address against its own MAC address, and notices.
Oh, sorry. It's a small hiccup here. Okay. I don't know why it has to load like this, anyway, as that is loading, basically what is happening is that the router, unlike the switches, the router does not broadcast messages. So the router receives the same frame, compares the destination MAC address 000B with the destination MAC address of the router 000D here, and notice that it's not a match.
MAC address, and notices that MAC address is in its MAC address table, so it sends it out just port 1. PCA receives the Ethernet frame, examines the destination MAC address against its own MAC address, and notices it is a match, so it receives the rest of the frame.
Can I have any questions there before I play the second video? You guys, you must know, when you learn in my class, you must know how to explain this concept, because that's why you are in my class. I don't mind if you are in another class, but my class, you must know how to explain these things. So can someone ask me a question? Okay. Or you guys will, the question will come much later. That's okay. So you have seen how the frame is being sent from PCA all the way to the router. So PCA goes to switch S1. Switch S1 examines the source MAC address. It's not in the table, so it stores it there with port 1. The frame is broadcasted to all the active ports. Active means any port that is connected to another device. The frame cannot be sent through S2, through number 2 port, and port is having nothing. So the frame will be sent through S3, to port 3, and also to port 4 to the next switch. Even if there were 1,000 switches connected to S2, all of them will receive the frame because the frame is a broadcasting device. The only device that does not broadcast traffic is the router. So S2 will receive the frame, examine the destination, the source MAC address. It's not in the table, so it will store it there. And then examines the destination MAC address. It's not in its table, so it will forward it to PCC and also to the router. PCC receives the MAC address. The destination is 000. It was initially 000B, and so it does not match, so it drops the packet. The router receives the frame, compares its MAC address with the destination MAC address, and it drops it. Now, we saw the time when the router now, we saw when the PCB is now forwarding, sending a reply back to PCA. So that is the time we're able to see when the source is now 00A. Sorry, the source is now 00B, which is PCB, and the destination is PCA, which is 000A. So as the frame is going from PCB, the source MAC address is 00B, and the destination is 00A. Switch S1 receives the frame. Because the source MAC address 000B is not on the switch, the switch is going to do what? The switch is going to store the MAC address of PCB because it is now the source 00B, and the port number is port number 3. Okay. When the frame is received by the switch cannot broadcast that frame. The only frame broadcasted is a frame that the destination MAC address is not in the table. Remember, the destination MAC address is 000A, and it is already in the table, so the frame is simply be sent through port number 1 that is paired with that particular port, and it goes like that. Now, let's see another video where now we want to send a frame to the default gateway and to see what comes back. All right, so let's see.
In this video, PCA is going to send a packet to the internet because the destination IP address is on another network. So in this case, the source MAC address is that of PCA. The destination MAC address is that of the router of 000D. So the Ethernet frame is sent to switch S1. Switch S1 receives the frame, examines the source MAC address, which is in its MAC address table. So it just simply refreshes the 5-minute timer. It examines the destination MAC address.
It refreshes the 5 minutes timer because the MAC address only stays in the MAC address table for 5 minutes and it has to be refreshed. That is what we call the 5 minutes timer. All right.
And because that destination MAC address is not in the MAC address table of switch S1, it floods it out all ports. PCB receives the Ethernet frame, and because the destination MAC address does not match its own MAC address, it does not accept the rest of the frame. Switch S2 receives the Ethernet frame, examines the source MAC address, which is in its MAC address table, so it also simply refreshes the 5-minute timer. It examines the destination MAC address of the frame.
Okay. So,
which is not in its MAC address table, so it floods it out all ports.
okay.
PCC gets the Ethernet frame, and because the destination MAC address does not match its own MAC address, it does not accept the rest of the Ethernet frame. The router receives the Ethernet frame, And because the destination MAC address does match its own MAC address, it accepts the rest of the frame. Now we'll look at the Ethernet frame coming from the router back to PCA. The source IP address is the IP address actually of a device on a remote network. The source MAC address is that of the router at 000D, and the destination MAC address is that of PCA. The frame is sent to switch S2. S2 receives it, examines the source MAC address, which is not in its MAC address table, so it adds it. It then examines the destination MAC address, which is in its MAC address table, so it forwards it out port 1. S1 receives the Ethernet frame, examines the source MAC address, which is not in its MAC address table, so it adds it to its MAC address table. It examines the destination MAC address, which is in its MAC address table, so it goes ahead and just forwards it out port 1 towards PCA. PCA examines the destination MAC address, and because it is a match, it accepts the rest of the frame.
Any questions, guys, about how the switch populates the MAC address table? It's a very important one. Okay. If there's no question, I'm gonna give you some. It's like a game here, but it's a simulation basically to make you to understand. It's called Switch It. You can note this in 736. So what's gonna here? You answer questions in 2 steps. You answer questions in 2 steps. You have the frame here, and the frame must have a source and destination MAC address. Then we have the MAC address table of this particular switch here. All right. So you have question 1, and then you have question 2 here. So let me do 1 or 2 before we get done. So the first one is let's see this frame here. This frame has a source MAC address of 0E and the destination MAC address of 0F. So 0E is this PC, and the source MAC address is 0F, and the destination is 0E. So source is this PC here. This PC here is the source MAC address, or the source of the traffic, and the traffic is going to 0E. 0E is the destination. Okay. Now we said that we have said what happens if the source and the destination MAC addresses are not to the table. Clearly, looking at the table does not have either of the 2 MAC addresses, 0E or 0F. What is here is 0B. So the first question, where will the switch forward the frame? So the switch, where will it forward the frame? When the switch receives the frame, obviously, because the switch does not have the destination MAC address, the switch will broadcast the frame out of all the ports. So which ports are active? F01 is active, F03 is active, F05 is active, F07 is active. This is a tricky one because they have included a hub here, which is a very funny one to deal with. This activity, if you don't get question 1, you cannot go to question 2, but you can check if question 1 is correct. Okay. Now, I don't know whether traffic will also come back to F09, since it will go back to F09, but because it's coming back to E0, it's coming to E2, I mean 0E here. So we are going to see. So the first thing we need to do, we know that the switch will forward the frame out of all the activity. It's actually broadcast the frame. So let me just check to see if it tells me in question 2, you answer for yes. If it tells you in question 2, yeah, that's how you know question 1 is correct. What am I saying? Let me remove one of the ports here and check. If I check, it tells me in question 1, the port you selected are not correct. It means your question 1 is not correct. So let me put back the 7, since it will be broadcasted to all the 7 ports. I click check. It now tells me in question 2, your answer for the switch, how the switch will handle the MAC address is not correct. So now I answer the second question. Tells me when the switch forwards the frame, which statements are true? The switch adds the source MAC address, which is currently not in the MAC address table. You know very well the MAC address of the source MAC address 0F is not in the table. That's why this statement is correct. Number 2, the frame is a broadcast frame and will be forwarded to all ports. It is not broadcast. Why? Because we know where it's going to. We know that the destination is E0. That's how we know it is not destination. It is not broadcast. So the frame is not broadcast. The frame is unicast frame and will be sent to specific port only. Yes, it is a unicast frame, but it will not be sent to a specific port because that port is not in the MAC address table here. That's why that answer is wrong. The frame is unicast frame and it will be flooded to all ports. So let's try these ones. Yes, the frame is unicast, but because we don't know the destination MAC address, it will force the switch to broadcast it to all the ports. The last one, the frame is a unicast frame, but it will be dropped at the switch. That is also not correct. So I click check here, and you can see you have successfully answered all questions based on the information in the frame and the MAC address table. This is one that requires you to have watched those videos clearly. And by the way, the two videos you can note this, please, our class rep. 734 is the first video, and 735 is the second video. Those two videos, you need to understand them to be able to understand what is happening here. Let me get a new problem. Now look at this very keenly now. The source of the traffic is 0C. And clearly 0C is on the table, MAC address table. The destination of our traffic, according to the frame, is 0E. And 0E is not on the table. So what's going to happen? Where will the switch forward the frame? We know that the destination is not known by the MAC address table. So the switch obviously will flood it to all the ports except where it has come from. So that means F01, the destination as a flooding. F03 is another active port. F0, the frame can never come to where it was originated. That's why we can't select F05. So if you select F07, and then we select F09, okay? F09, so it will be flooded to all the ports except the incoming port. So if we check this, let's try and check. It should tell us in question 2. Very good. So we know question 1 is right. So we now go to question 2. We know that the source of the frame is already on the MAC address table. So which means the switch will add the source MAC address. It will not be added. The switch will add the source MAC address, which is currently not in the table. No, it is currently in the table. So we will leave that. Once it is in the table, now we go to the type of the frame. Of course, the frame is unicast because you know it is going to a destination of E0. So the frame is actually unicast frame, and it will be sent to a specific port. It cannot be sent to a specific port if that port is not on the MAC address table. So the frame, yes, is unicast here, and it will be flooded to all ports, correct. The frame is unicast, and it will be flooded to all ports. And I check my work here, and it's correct. Now, as you play this game, ladies and gentlemen, you'll also come to a time when the frame is unicast, but it will be, let's say a frame is broadcast, and it will be forwarded to all ports. That only happens if the destination MAC address is FF. Anytime the destination MAC address is FF, you and I were able to learn today that FF is a MAC address is a broadcast MAC address where it is used to communicate from one to all. From one to all. All right. All right. So do this, play around with it, make as many mistakes as possible, and keep on varying. Check if your first question is correct before you can go to the second question. That's activity on 736. 736. All right. So that was a good one, guys. And now, what I want to do right now is that I want us to finish the remaining bit of the remaining bit of this chapter here. And I'm gonna share the whole screen now. And I'm gonna bring up my slide here. Okay. So we have covered everything we needed to learn in the next few parts of the slide, examining the source and the destination of all that we have talked about. And now we need to talk about switch speeds and forwarding methods. Switch speeds and forwarding methods. We have two frame forwarding methods used by Cisco switches. The first one is called store and forward. Store and forward. And the second one is called cut-through switching. So we have store and forward switching and cut-through switching. Now, we have learned before that as frames and packets are being sent over the network, they are normally broken down into small units that we call segmenting. We call it segmenting. It is segmented into small units. Now, in store and forward switching, this is a method whereby the frame must receive the entire frame, all the units of the frame, before it begins to forward it. Remember, PCs send frames to the switch, and then the switch forwards them to the router, and that's how they go to the internet. All right. So the frame must receive the entire frame, and during the process of receiving that entire frame, or the major reason why it wants to receive the entire frame is basically to check for any errors using what is called CRC. Cyclic redundancy check. Cyclic redundancy check. I can give you a good example of CRC. Let's say I want to send you an email. For example, I send you an email. I'm using a very local. I want to make this as simple as possible for you guys to understand how error checking is always done between two computers. So I send you an email message, but the message I'm sending you, I also accompany it with a mathematical question. Let's say a mathematical question. All right. So this mathematical question, I calculate it. I calculate the question, and I also attach for you the answer. I attach for you the answer, and then I send you the message. Now, when you receive the message, I want to check if someone was able to hack into our communication and modify the mathematical question I sent you. Because if the question is modified, then if you calculate the question from your side after receiving the email, then obviously your answer is not going to be the same as the answer I sent you. All right. So I sent you the equation. I tell you, please calculate the question and compare the answer you get with my answer. If you get the same answer as the one I sent you, that's how I know no one modified or no one hacked into our messaging. But if you get a different answer from the one I sent you, then we know that that message was corrupted and you're not going to reject it. And that's what we call cyclic redundancy check. Now, that is store and forward switching. It must receive the entire frame and compute the CRC before it begins to forward it to the next port or to the outgoing port. The second method is called cut-through switching. Cut-through switching is a method whereby the switch begins to forward the frame even before it has been received entirely, before the switch receives the entire frame. So long as the frame has learned from one of the units the destination MAC address. The minimum the switch needs to know is the destination MAC address. Once it has known the destination MAC address, the switch begins to forward the frames even before receiving the entire frame. Now, the major advantage of store and forward is that frames are forwarded without any errors, okay? Because the errors will be detected and the switches are going to discard the frames, okay? And that is why store and forward is required in something we call quality of service, QoS. We'll get to learn more about it in the last module. And of course, even quality of service, which of course works with voice traffic used by voice over IP traffic, so on and so forth. So QoS basically is the process of giving priority to some traffic unlike others, some traffic unlike others. That is QoS. Now, it's important to note that the second method, which is called cut through, is divided into two more methods, two more subgroups, or two more variants. All right? You know that cut through does not perform any error checking. A switch using cut through switching does not do any error checking. So the first method of cut through is called fast forward switching. So fast forward switching, this is actually the typical, it's actually the typical cut through switching method. It is the typical cut through method. Why? Because after it has read the destination MAC address, it immediately begins to forward the frames. Okay, it starts to forward the frame upon receiving or upon knowing the destination MAC address. Then the second method of cut through switching is called fragment free switching. In fragment free switching, the switch begins to forward the frame immediately after it has received the minimum size of a frame. And what was the minimum? The minimum was 64 bytes. The minimum was 64 bytes. Okay? The minimum was 64 bytes. The minimum was 64 bytes, and that is so fragment free switching. It wants to wait for the first 64 bytes. Why 64 bytes, by the way? It's because most errors normally occur within the first 64 bytes of the frame. Most errors, either they are network errors or they are collision errors, they normally occur within the first 64 bytes. Now, let's talk about something as we finish, something called buffer memory. Buffer memory. And we hear this word a lot called buffering. Buffering. The network is buffering. So the word buffering comes from what's called the buffer. And the buffer is a kind of a temporary memory. It's a temporary memory found in the switches, which temporarily, it actually is not a temporary memory, but it's a memory that temporarily stores the frames as they come into the switch before they are processed by the MAC address table and they are forwarded to the next device along the network. So it's a frame, it's a memory which temporarily stores the frame before they are forwarded to the next device. So we have what is called a port-based memory and the shared memory. Now, a port-based memory, I can give you a very good example. When you go to the hospital, some hospitals have enough space. And so there will be a room where people will be waiting, like a waiting room. All right? A waiting room. So some hospitals do not have the waiting room. And so people will wait on the queue. Exactly. So the port-based memory is whereby the frames are queued on a particular interface, on a particular port or interface, and then as they're being processed to be forwarded to the next device. That is the port-based memory. The frames are queued on the port. The shared memory is like the hospital with the waiting room, where the frames are queued or they are stored on a common memory or a shared memory, and then they are processed and forwarded to the next device. So that brings you to, when you go to buy a switch, make sure that is one of the specifications that you consider when buying a switch. The switch needs to have a larger buffer memory so that, because smaller buffer memory are the ones that can cause your network to slow down, because we'll have more frames to process, but less memory to temporarily store them as they're being processed. Okay, so make sure buy a switch with a large buffer memory so that even if the the memory, I mean, if the memory is bigger, then it cannot fill up, and so it means it can store more frames as they're coming and as they're being processed moving forward. We already talked about duplex. Duplex switches also have duplex settings on their interfaces, okay? And it is important that two switches connected together need to be set to the same duplex. Either you set it to full or half. If you set them to full half, there'll be a collision. Why? because the full duplex port can send and receive traffic at the same time, but the half duplex, it can only send or receive. So if you try, if it is receiving, no, if it is sending and the other switch try to sending back to it and it is sending itself, then there's going to be a collision, and collisions lead to errors within the network, and that will slow your network connectivity. So most devices currently have a full duplex. Most of them normally have a full duplex. And that also goes to speed. Switches, you need to have the same speed on both ends. We need to have the same speed. If one side is 100 Mbps, the other side needs to be 100 Mbps. If one side is 1000 Mbps or 1 gigabyte per second, then the other side needs to be the same. Okay? You've heard of what is called a bottleneck. A bottleneck can be formed when a port of a higher speed is trying to send traffic to a port of a lower speed. Then that is going to form some collision or a bottleneck within the network. I did talk to you guys about MDIX, auto MDIX. And this, you can remember when I was talking about the copper straight through, copper crossover. How do you make the two cables? You need to arrange the 802.1x, no, not the 802.1x. You need to arrange what is called the how do you call it? I mean the arrangement of the A and the B's. I forgot the number. So, sorry? Say that again.
The T638 and 658, sorry.
The 656, is it 658? Anyway, that number, I mean, you can revisit it. The T568, exactly. The T568A and the T568B. Good. So I told you, when you want to make the crossover cable is used for connecting same devices. The two ends of the cable must be different. When you want to make the copper crossover cable for connecting same devices, the two ends must be different on how you arrange the T568A and T568B. Then I talked about auto MDIX, which is currently being used such that you don't have to create a crossover or straight through cable. You can actually use any of the cables to connect any devices, because the devices have a feature called the automatic medium dependent interface crossover. Automatic medium dependent interface crossover, which will automatically sense. They will automatically sense the cable and detect it and complete the connection for you. That is the auto MDIX. We will be configuring them soon enough. Now, I want to end there for today, but normally I don't end without any question from the floor. Can I get any questions from the floor, please? All right. If there's no question, then I think we end it there, and